afternoon.
Hello, Elizabeth. I've been expecting you. What brings you in today?
Well, I have some concerns about the growth of my baby and my placenta. Hopefully you can answer my questions.
Of course. I've prepared some paperwork which you can look over while we talk about it.
Okay, thank you.
So, as you know, the data that we have collected is presented in a derivative form with units grams per day. First, we're going to discuss the fetal growth.
Okay.
So, this figure represents the fetus growth in grams per day. On this graph, you can see the function of the fetus growth.
How do you know that this graph is a good fitting?
Well, this graph is a good fitting because the r-squared value equals to 0.834, which is very close to 1, which means it is accurate.
What is the meaning of this function?
Well, this function and the meaning of it is to show the rate of change. It is the velocity, meaning it is the growth of the weight of the fetus as a function of time. On this graph, we can see the second derivative of the fetal function, and this graph also shows the inflection points.
What does the inflection points represent?
Well, the inflection points represent the concavity change. As you can see, we have 3 inflection points. Before the first inflection point, the rate of change of the fetal function is increasing at a decreasing rate, meaning that the rate of change for the growth of the fetus is increasing, which means that the fetus is growing. However, it is increasing at a decreasing rate, which means it is a slower rate. And then after the first inflection point, the concavity changes from concave down to concave up. Before the second inflection point, the rate of change of the fetal function is decreasing at a decreasing rate. The acceleration of the fetus is decreasing at a decreasing velocity. During this time, the fetus was born. Then after the third inflection point, the rate of change is increasing at an increasing rate. This is the time when the baby was born, and its rate of growth was increasing at an increasing rate. Now we're going to talk about the placental growth. This figure represents the growth of the placenta in grams per day. It is represented the growth of the placenta as a function of time. It represents how fast the placenta is growing at a particular time, which means it is the instantaneous rate of change. This figure here represents the second derivative of the placental function with the inflection points. As previously said, the function has 3 inflection points. Before the first inflection point, the rate of change of the placental function is increasing at a decreasing rate. Before the second inflection point, the rate of change of the placenta is decreasing at a decreasing rate. And the function is decreasing its acceleration while decreasing the velocity rate. After the second inflection point, the function is increasing at an increasing rate. The rate of change of the placental function is increasing at an increasing rate. Now we're going to compare the placental and the fetal inflection points. On here we can see the placental, and on here we can see the fetal inflection points. The inflection points occur at the same time for the first inflection point. And as we can see, the second, the third inflection point occur at different times with a big gap. Now we're going to talk about the antiderivatives. In order to find the antiderivative, we can use the expression t to the n plus 1 divided by n plus 1. Therefore, we're going to have the values, and in order to find the constant, the last number, we need to plug in the number of time for t and set it equal to the amount of grams.
Okay.
That's how we're going to find the antiderivative.
Alright. You just answered my question about what an antiderivative means. Great.
And this function is the antiderivative for the placental function. So as I said previously, we can find it by using an expression, and we can plug in the time and set it equal to grams in order to find the constant. The antiderivative is the original function
Okay.
of the growth of the placenta for the fetus. Okay, so this graph is the graph of a study that was conducted to examine the placental volume for non-exercising mothers.
Okay. What is the volume at time 0 and how can I find it?
Well, the volume at time 0 would be 0. In order to find that value, you would need to plug in 0 in the function for every t that you have in the function. So when you plug in the 0, you would get a value of 0, which means there would be the volume of the placenta at time 0 would equal to 0 milliliters.
And why would that be?
Well, the explanation for that is that at time 0, the placenta is not existing, so that makes sense that the volume of the placenta is 0.
Do you trust the data?
I do not trust the data in the volume of the placenta experiment because no details were provided, only the numerical data was provided. And when we match the two studies, the placental volume inflection point does not match the same time period as the placental weight from our data. The placental volume inflection point occurs around 6 weeks, while the placental weight inflection point occurs around 17 weeks.
Is there a medical explanation for why my placenta and my fetal second and third inflection point occur at a different time?
Yes, of course there is. The meaning of that is because the inflection point for the fetal and the placental growth were different for second and the third inflection points, because as it was mentioned in the article, after birth the placenta stopped growing while the fetus continued to grow. That's why we see that the placental inflection point and the fetal inflection point have a gap between them. When the baby was born, the placenta was no longer needed. Does that explain your questions?
Yes, thank you so much, doctor.
Thank you for coming in, Elizabeth. Have a good day.
You too.